Albert Einstein once said, "One may say the eternal mystery of the world is its comprehensibility." Indeed, one of the most fascinating things about our universe is the fact that it is knowable by us. It didn't need to be so. How is it that the universe we grew up within, in all of its incredibly vast complexity and seemingly infinite expanse, allows itself to be understood by tiny creatures like us on an ordinary little world called Earth? But alas, knowable it is. And not only is our universe's vast spatial expanse understood, but its entire history is laid bare for us to observe as well. We just needed time to develop the correct eyes and ears to fully grasp what we've been privy to all along. Let's start from the start. How did our universe begin? That's what we'll be discussing in this video of Turtles All the Way Down. The history of astronomical investigations have been slowly but surely pointing to one undisputable answer to the origin of our universe. That is, that it had a beginning about 13.8 billion years ago, and that it did so in an unimaginably dramatic way. This beginning is what is termed the Big Bang. Science didn't always have this as the answer to our cosmic beginning, and in fact held to an entirely different idea. The steady state theory, for example, was popular among many astronomers before evidence mounted for the Big Bang. The steady state theory claimed that the universe had always existed and had no beginning, but instead the matter in the universe was steadily being created in the voids between the stars and galaxies. Other hypotheses saw the universe in an infinite cycle of birth, expansion, collapse, and rebirth. But science never works in absolute certainties. It only operates in probabilities. So when a claim in science is made, it can never be proven at 100% certainty. That's the domain of mathematics. Claims, evidence, and theories can exist arbitrarily close to certainty, but never reach it. What this means is that even though the currently best scientific theories we know of, such as the Big Bang, evolution, and general relativity, are almost certainly true in their explanations, there is still some wiggle room in their details. Astronomers and cosmologists overwhelmingly agree with the essence and validity of the Big Bang, but many may dispute some of its finer points. Did the universe begin about 13.8 billion years ago in a violent explosive event? Yes. Did it start from an infinite singularity? Maybe, but maybe not. So how can science now be so sure that the universe had a beginning, and that it did so in the spectacularly violent way that we call the Big Bang? Several great lines of astronomical evidence have pointed directly to an energetic and explosive event at an exact point in our past. One was the surprising finding by Edwin Hubble in 1929 that the universe is expanding in all directions. This idea was theorized earlier from Einstein's general relativity, but was brought to light observationally with Hubble's findings of redshifts in the light from distant galaxies. The shifting in light spectra indicates an object's speed away or toward the observer. It will be blue shifted if the object is moving toward, and red shifted if speeding away. The amount of the shifting in that light spectrum determines how much velocity the object has. What Hubble found was that the further away galaxies are, the greater the redshifts were found to be. In other words, there is a linear relationship between distance from us and speed away from us. The crucial point, though, is that this is true from every point in the universe. So if you happen to be on a galaxy billions of light years away from us, you too would see all the galaxies around you moving away as well, and in the same way that we see them. This indicates a universal expansion. For more visuals and information on this idea, see a previous video of Turtles All the Way Down, where we discussed what dark energy is. It's very important to note that this expansion is an expansion of space. That is, the background fabric that objects, such as stars and galaxies, are embedded within. It is not the objects themselves that are rushing away from each other while the space between them is unmoving. It is just the opposite idea. Like pulling a rug slowly while a chair sits on top of it. The chair moves, but only because the carpet under it is moving. So, some event in the universe's past produced its spatial expansion, and it has been doing so ever since. The Big Bang model predicts this expansion, and we experimentally find it existing. If we were to rewind the tape of time and observe what happened within the universe, we would find that all large objects become closer and closer to one another. But the surrounding ambient temperature of the universe will also be increasing. As the contraction continues and the temperature rises, there will be a point when the thermal radiation from all of the condensing matter reaches an important threshold heat, where electrons can no longer remain bonded around the nuclei of their atoms. Atoms disintegrate, leaving behind free electrons and nuclei made up of protons and neutrons. The universe becomes a plasma of thousands of degrees. These are the temperatures at the surface of our sun, and this is the state the universe found itself in about 378,000 years after the Big Bang. It is at this stage in the universe where it was right on the verge of recombining electrons and nuclei to form stable atoms. The surrounding radiation was constantly bouncing from charged particle to charged particle and scattering everywhere. If we were to run our universal movie forward again from this point, we begin seeing stable hydrogen and helium atoms forming, and a bunch of scattered and unabsorbed radiation all over the universe, giving it its thermal bath. The temperature of this radiation would be around 3,000 Kelvin. However, as the universe expands, this background radiation cools. This is because its wavelengths stretch with the expansion of space. If you stretch the wavelength of radiation, you start from high energy and stretch to lower energy. Arriving at the present universe, this background radiation would be at a chilly 3 Kelvin, at wavelengths in the microwave range. Indeed, we find this so-called cosmic microwave background radiation still bathing the entire universe. It was accidentally discovered by astronomers Arno Penzias and Robert Wilson in 1964. This is yet another major piece of evidence for the Big Bang. The Big Bang model again predicts this background radiation, and we experimentally find it existing. If we rewind our universal time machine to even earlier times than when the cosmic microwave background radiation began, we will find exponentially higher temperatures and reach those that will be in the millions of degrees. Temperatures found at the center of our sun where nuclei themselves begin to break apart. The universe will be immersed in a plasma of free protons and neutrons, along with all of those scattering electrons and photons. The energy of the protons and neutrons will be such that they will constantly be colliding, binding into nuclei, and promptly breaking apart again. But roll the film forward again and the universe expands. The background radiation cools, and these nuclei become more stable. The cooled and stable nuclei that will remain will be the easiest ones to make, hydrogen and helium, with trace amounts of lithium, and all in specific concentrations. When astronomers take a universal inventory of elemental abundances by observing and cataloging spectral lines, it is found that our universe's elemental percentages line up identically to what models of the Big Bang predict, when also considering the formation of heavier elements within stars. Namely, hydrogen makes up 74% of the universe's normal matter, while helium makes up 24%. I say normal matter because there is still the mysterious dark matter and dark energy, which comprises most of the matter and energy of our universe. We discussed both of these ideas in earlier videos here. The Big Bang model predicts these abundances, and we observationally find them existing. Models for the Big Bang and its subsequent universal history predict that galaxy formation would occur within 1 billion years after its beginning. Star ages and compositions should change from almost entirely hydrogen at the early stages of the universe to those that consist of heavier elements. Additionally, the types and morphology of galaxies would proceed in a somewhat orderly fashion. Finally, the Big Bang model forecasts eventual galactic structures and clumpiness across the universe. Every single one of these predictions has been borne out by the data. The Big Bang model predicts these evolutions and structures, and we observationally find them existing. Right after the age when the background temperature dropped below the threshold, when stable atoms could form, again around 378,000 years after the Big Bang, the Big Bang model predicts that those condensed atoms should have formed primordial clouds of simple elements, such as hydrogen and helium. Just vast and simple clouds without any structure. Do we find these at the earliest ages of the universe? In other words, at the greatest observable distances from us? Indeed, we do. Because of their gossamer natures and great distances from us, it was very difficult to discern them. But in 2011, astronomers began finding them. Again and again, the Big Bang model predicts very specific objects and events, and we observationally find them existing. If it looks like a duck and it quacks like a duck, then it must be a duck, right? Okay, so if we can accept the model of the Big Bang, then we are still faced with an obvious question. What caused it? What lit the fuse that produced the bang? I must say at the outset that absolutely no scientist working on this problem has an answer yet. We admit our ignorance at this stage. The reason is twofold. One, as of yet, we have no science of quantum gravity, which I'll touch on in a second. But two, we know that from general relativity, that we run up against a time boundary at the beginning of the universe. First, quantum gravity. We currently have two remarkably accurate models of the physical world in our physics. The first one is Einstein's theory of general relativity, which describes how matter, space, and time interact with each other to create gravity. So this theory works extremely well in the large regimes where stars, galaxies, and the entire cosmos's evolution live. The other model that we have available, which happens to be the most accurate of any theory yet proposed, is that of quantum theory, or more specifically, quantum field theory. This is what fully describes how matter, energy, and forces interact. While its functioning is mostly operative at subatomic scales, it actually describes how the entire universe really works at its most fundamental level. Taken together, both general relativity and quantum field theory describe the world almost entirely. However, we know these two cannot be the end of the story, as they completely leave out dark matter in their descriptions, among other things. Additionally, if they are to describe the true world, they must somehow be unified in their pictures of the world. They do not. The holy grail of physics is the dream of unifying these two theories in what is called a theory of everything. In other words, quantum gravity. Neither one of these theories work at the extremes of gravity, called singularities. And there are two places in nature where singularities potentially occur: in the centers of black holes and at the beginning of the universe, at the Big Bang. We can potentially describe the natures of these regimes arbitrarily close to their singularities, but not at the singularity itself. Another way of saying this is science cannot yet tell us what happens at the center of a black hole, nor at the very start of the Big Bang. The other issue with answering the question of what caused the Big Bang is the one about a time boundary. This relates to the quantum gravity problem, but is specific to general relativity. When we rewind the tape of time and get closer and closer to the Big Bang singularity, we find that more and more matter and energy is being squeezed into a smaller and smaller volume. The universe is shrinking. General relativity says that as more energy is confined within a smaller volume, the space-time around it warps and bends, which is precisely what gravity is, the warping of space. But remember that it is not just space that is warping, but time is as well. But what does the warping of time mean? In this case, it means the slowing of time. What happens if you continue this crushing process of universal compression? Gravity continues to increase, but so too does the dilation or slowing of time. We reach the singularity of the Big Bang. What happens there? If general relativity were to work at that point, it would predict that time actually stops and gravity becomes infinite. Let me reiterate. Time stops at the Big Bang singularity. There is no more time. The clock has stopped. So the questions of what caused the Big Bang or what happened before the Big Bang have absolutely no meanings, as answering them requires there to be some sort of time before the singularity. That time doesn't exist. As the amazing physicist Stephen Hawking once said, asking what happened before the Big Bang is like asking what's north of the North Pole. The North Pole is the northernmost point. There is nothing more north than that. It's a meaningless question. Everything began at the Big Bang, including time itself. However, this hasn't stopped some scientists from trying, because as I've said, the two great theories we do have do not work well at these extreme regimes around singularities. So some scientists have pointed to the fact that gravity acts like a kind of negative energy that cancels out the rest of the normal energy within the universe, which comprises matter and radiation. If this is so, then the Big Bang started with a net zero energy. It has no need to explain where all of the energy that started it off came from. Many scientists also zero in on quantum mechanics' Heisenberg uncertainty principle to help explain the cause of the universe. This principle states that there is an inherent uncertainty in the amount of energy and the amount of time under consideration. The more precisely you know of one, the less precisely you know of the other. For example, if you were to precisely measure a certain amount of energy, you will give up on a precise knowledge of how much time it took to measure it, and vice versa. This has dramatic consequences for the entire universe. Given an arbitrarily uncertain amount of time, you can end up having an arbitrarily large amount of energy, a Big Bang, and a universe of energy, say. This too would explain the origin of our universe. As an extension to this idea is the theory of cosmic inflation, where the universe had a very short and early period where it expanded exponentially from a tiny point and then calmed down to the usual slower expansion we find ourselves in today. The cause of this inflationary expansion was from the decay of a so-called false vacuum into our true vacuum. The pent-up energy this created produced all of the matter and energy we see today. But notice what these origin of the universe hypotheses do. These attempts presume existing fundamental laws of physics to explain the origin. However, they do not explain the actual origin of the laws themselves. If this seems unsatisfactory to you, well, then I would have to redirect you to philosophical or even religious explanations for those, as it seems as though science may not even in principle be able to explain away these most fundamental layers of reality. Science would be asked to lift itself up from its own bootstraps. We may just have to be content with brute facts about the universe that bottom out at the laws or mathematical frameworks themselves. Watch our earlier video where we discussed why there is something rather than nothing, in which we talk about these ideas in more depth. But there may still be another way scientifically. Wait for a theory of everything. Wait for quantum gravity. This may be our long hoped-for explanation for where even the laws of the universe come from. It's the big hope that may truly explain the Big Bang. How did our universe begin? Our current best model is the Big Bang, the greatest explosive event in the history of the cosmos that created all the energy and matter in the universe about 13.8 billion years ago. There are no other contenders that even come close to explaining the origin of the universe. Just a side note to say that the theory of cosmic inflation is just an extension of the origin of the Big Bang model, for those who may take issue with there being no contenders to the Big Bang. So I include inflation as part of the Big Bang paradigm. The evidence for the Big Bang is overwhelming, and it continues to come in. Its subsequent evolution produced all the structure and variety that we see around us, all while the universe continues to expand and cool. The question of what caused or started the Big Bang is currently an unanswered one and may even be an unanswerable one. There have been attempts at explanations, but most entail pre-existing universal physical laws. Can these too be explained away? Quantum gravity may be the key. Thanks for staying with me and turtles all the way down. Please consider supporting this channel by simply subscribing and viewing our discussions on these big questions. I really appreciate it. Until next time, stay safe and stay curious. And bye for now.